Hi everyone, this is Mr. Bowman, and this is the last lesson for chapter 14, and it is tree diagrams with the general multiplication rule. If you recall, we talked about the general multiplication rule on the second day of this chapter, and it says if I want to find the probability of A and B, I can take the probability of A in blue and multiply it by the probability of B given A. What we're going to do is we're going to talk about tree diagrams and use that general multiplication rule in finding some probabilities with the tree diagram. So we're going to take a look at this example, and then I'm going to illustrate this example with a tree diagram. Room draw is a process for assigning dorm rooms to students. When students have equal priority, they are randomly assigned to the rooms that are available. When it is time for you and a friend to draw for a room, there are 12 rooms left. 3 are in Gold Hall, very desirable. 4 are in Silver Hall, not as desirable. And 5 are in Wood Hall, not desirable at all. You get to draw first, and then your friend will draw. Clearly, your draw and your friend's are dependent, or not independent. Another way of saying that is your friend's chance of drawing a particular hall depends on what happens on your draw. So we're going to illustrate this with a tree diagram. So your friend's going to, you're going to draw first, and we are going to have 3 possible outcomes for you. So this is the first stage of the tree diagram. There is Gold Hall, Silver Hall, and Wood Hall. And we know that there are 3 in gold, there are 4 in silver, and there are 5 in wood, so that's a total of 12. So there's a 3 out of 12 chance of you drawing Gold Hall. There's a 4 out of 12 chance of you drawing Silver Hall, and a 5 out of 12 chance of you drawing Wood Hall. Now that you go, your friend gets to go, and your friend is also going to have 3 possibilities, regardless of what happens for you, but the probabilities for those 3 possibilities are going to be different depending on what happens for you. So this is your friend's stage of the tree. And we know that there are only going to be 11 possibilities left in each case. So we're going to put our denominators here for all of these. And then we're going to fill in the corresponding probabilities. So let's write down gold, silver, and wood, the 3 probabilities or the 3 possible outcomes for regardless of what you draw. Silver, wood, gold, silver, and wood. Okay. So the first stage of the tree, the 3 twelfths, 4 twelfths, and 5 twelfths, are the probability of you drawing a gold, a silver, or a wood. The second stage is going to be the conditional probabilities. So given that you've drawn gold, the top branch, what is the probability that your friend also draws gold? Well, there would be 2 gold left out of 11. Given that you've drawn gold, what's the probability that your friend draws silver? There would be 4 silver still left out of 11. Or given that you've drawn gold, what is the probability that your friend draws wood? There are 5 left out of the 11. And then we're going to do 3 more conditional probabilities. Given that you've gone the middle branch and you've drawn silver, what's the probability that your friend draws gold? Well, there would be 3 golds still left out of 11 total. Given that you've drawn silver, what's the probability your friend draws silver? There would be 3 silvers left out of 11 silvers. And given that you've drawn silver, what's the probability your friend draws wood, there are 5 wood left in those circumstances out of the 11 total left. And finally, we're going to look at the conditional probability if you have drawn wood. So given that you've drawn a room in Wood Hall, what's the probability that your friend draws a room in Gold Hall? Well, there's still all 3 Gold Hall rooms left out of 11. Given that you've drawn Wood Hall, what's the probability your friend draws Silver Hall? There would be 4 left out of 11. Let me write that in a little bit better. 4 out of 11. And given that you've drawn Wood Hall, what's the probability that your friend also draws Wood Hall? So there would be a total of 4 left out of 11. So that second stage are all conditional probabilities. And at the end of those, you can find the following. You can find the probability of gold and gold. Well, that would be the probability that you draw gold times the probability that your friend draws gold, given that you've drawn gold. And what you do is you just multiply as you go out the branches. So the probability that you both draw gold would be equal to 3 out of 12 times 2 out of 12. Likewise, if you wanted to find something like the probability that you draw silver and your friend draws gold, then you can say, well, that's the probability of silver and gold, which is equal to the probability that you draw silver times the probability that your friend draws gold, given that you've drawn silver. And that would be, again, just multiplying the probabilities. The probability of you drawing silver times the probability of your friend drawing gold, given that you've drawn silver. And we can go out along any of those branches and find those probabilities of gold and gold, gold and silver, gold and wood, etc., using the general multiplication rule. So I want to go back and point out some things that are true about all tree diagrams. Number one is if you are traveling out the branches, you multiply, and if you are traveling across branches, you add. So traveling out branches is and, or corresponds to and traveling across branches corresponds to or. Another thing that is really important is at any stage or any place where it branches, the probabilities have to add up to 1 because it accounts for all the possibilities. So 3 twelfths plus 4 twelfths plus 5 twelfths is 12 twelfths. Likewise, at this branch, 2 elevenths, 4 elevenths, and 5 elevenths is 11 elevenths. 3 elevenths, 3 elevenths, and 5 elevenths is 11 elevenths. 3 elevenths, 4 elevenths, and 4 elevenths is 11 elevenths. Same thing would be true if we found all these probabilities out here at the end and we added them up. That would account for all the possible outcomes at that point in the tree diagram, and they would add up to 1 as well. So we've already effectively done B and C up here, so we're going to skip to D. It says show that your draw and your friends are dependent. So let's pick 2 outcomes. The probability of silver for you and gold for your friend. Okay? If that is equal to the probability of silver times the probability of gold, then they're independent. Okay? So how are we going to find the probability of silver and gold? We're going to go back. Probability of silver and gold, well, that's our blue line there. Silver, gold is 4 twelfths times 3 elevenths, which turns out to be 12 over, let's see, 11 times 12. What is 11 times 12? That is 132. And that's often easier to convert to a decimal, so we're going to convert that to a decimal. 12 divided by 132 turns out to be 0.09 repeating, so 090909. And now we're going to go back over here and we're going to write the probability of silver and times the probability of gold. Well, probability of silver is what? There are 4 silver out of 12, and the probability of gold, there are 3 gold out of 12. So this would be probability of silver, which is going to be, what did we say that was? 4 out of 12 times 3 out of 12, which is equal to 12 out of 144, which reduces to 1/12, which as a decimal turns out to be 1 divided by 12, 0.083, repeating, so 0.08333. That is not equal to, those are not equal. Okay, probability of silver and gold, so they are not independent. If you wanted to do that with conditional probabilities, you could as well. So here's what I'd like you to do. I'd like you to pause this video and do question A, and we're going to start with the first branch of the tree diagram being the goals. So draw me a tree diagram, label it, put the probabilities on there, and then unpause the video and take a look at it. So this is what the tree diagram would look like if you were filling it out for this particular example. One thing I do want you to notice is that I made things easy for myself. We don't normally write fractions like I'm highlighting here in yellow, but there's nothing wrong with that. You can easily convert that to a decimal. And then if you want to find the probability that a randomly selected student thinks grades are the most important and they are male, you can multiply this times this, and that's that work right here, and get that probability right there. So this is the same example that we did on the second day of this chapter, and we already know that the goals and gender are independent of each other, but we can prove that. We can prove that in different ways. So one of the ways that we can do that is we can take a look at the tree diagram and show that the probability of A times B is approximately equal to the probability of A and B. We did it the other way using conditional probability back on the second day. So pick one of the outcomes from one of the variables and then pick another outcome from the other variable. So we could say the probability of male and sports, or probability of male times probability of sports, should be equal to, that's the question we're asking, the probability of male and sports. So we'll figure that out in just a minute here. So probability of male is going to be 0.475. So we'll go back to the previous page, 0.475. We're going to multiply that times the probability of sports. Probability of sports, as you can see, is 0.188. So we'll go back, multiply that times 0.188. And is that equal to the probability of male and sports? So male and sports from the table is 0.090. So are those equal? 0.090. And if you take your calculator and take 0.475 times 0.188, you will get 0.0893. 0.0893. And that's approximately equal to 0.090. Remember, our rule was if they're within 0.02 of each other, then we'll call them independent. So therefore, we say they're independent. All right, that's it for tree diagrams and the general multiplication rule. You can now start your homework.